Welcome to the Bodhi Academy. My name is Amisha Kulaso, and in today's video we'll continue the chapter 5, class 11, Thermodynamics. So in today's video we will learn about the different enthalpies that are present for different types of reactions. Okay, so to begin with, let's talk about the standard enthalpy of combustion. So now we know combustion reactions, they are exothermic in nature. Now, what is this combustion, standard enthalpy of combustion? So, standard enthalpy of combustion, it is defined as the enthalpy change per mole of a substance when it undergoes combustion and all the reactants and products being in their standard states at a specified temperature. So, we are saying that here, whenever there is a substance, okay, it is the enthalpy change that happens per mole. Per mole of any substance when it undergoes combustion, and all of the reactants and products that are present over here have to be in their standard states at specified temperature. Examples of this would be: during complete combustion of 1 mole of butane, 2658 kilojoules of heat is released. Now this thermochemical reaction, if we break down, we have butane plus we have oxygen, which gives us carbon dioxide plus water. So over here the combustion that is there, it is minus 2658.0 kilojoules mole inverse. Remember that for combustion it is always going to be in negative, the enthalpy is going to be negative. Another example, if we look at, we have combustion of glucose that gives out around 2802 kilojoules mole of heat, for which the overall equation is given as glucose plus oxygen giving carbon dioxide plus water. Again, the enthalpy of combustion is minus 2802.0 kilojoules mole inverse. Next, we have enthalpy of atomization. Now for this, let's consider a simple example of hydrogen gas which is getting dissociated. Okay, it is giving us two atoms of hydrogen, not molecules. You can see that hydrogen atoms are formed by breaking the hydrogen bond in the dihydrogen. This is the dihydrogen. So the enthalpy change in this process is known as enthalpy of atomization, and it is given by delta subscript A H naught. Now in this, we say that it is the enthalpy change of breaking 1 mole of bonds completely to obtain atoms in the gas phase. So here we are considering the amount of enthalpy change that is required to break a bond, okay, to break a bond in such a way that and to break it completely in such a way that we obtain atoms of that molecule in the gaseous state. For this, if we look at examples, another very important thing to remember here is that here we can say that the enthalpy of atomization is same as the enthalpy of bond dissociation. Okay, so here if we look at another example, we have methane, which is giving us carbon plus hydrogen. For that, atomization energy is 1665 kilojoules mole inverse. So here also again this molecule of CH4, it is breaking down and we are getting two different atoms, one atom of carbon and four atoms of hydrogen. So here also what we notice is that bond dissociation. Bond dissociation means what? Again, it is breaking of bonds itself. So here also we are able to get bond dissociation. This is same as bond dissociation. So therefore we say that the enthalpy of atomization is also the bond dissociation enthalpy. Next, let's look at the bond enthalpy. This is given by delta subscript bond H naught. Now, for any chemical reactions that involve the breaking or the formation of chemical bonds, there is some kind of energy that is required to either break that bond or to form that bond. So it is possible that we relate heat of a reaction to changes in energy associated with either breaking or making of chemical bonds. With reference to the enthalpy changes associated with the chemical bonds, we can define two different terms that are used majorly in thermodynamics. First one is the bond dissociation enthalpy and second is the mean bond enthalpy. So now we will understand what is this bond dissociation enthalpy. So now when we talk about diatomic molecules, like previously we took the example of this hydrogen here, H2 going to 2 atoms of hydrogen. So in this case, what we see is that the bond dissociation enthalpy, it is the change in enthalpy when only one mole of covalent bond of gaseous covalent compound, it is broken to form products in the gaseous phase. That is what we notice here. We have a covalent bond between these H2 diatomic gas. Here we have H2 that is covalently bonded. Then it is breaking down to form two compounds that are also covalent. We will have H plus and H plus, correct? So that is what is about bond dissociation enthalpy. Similarly, if we take another examples, we have chlorine breaking down into 2Cl, oxygen breaking down into 2O. So in all these cases, polyatomic molecules, bond dissociation enthalpy is different for the bonds within the same molecule. Now when we talk about polyatomic, so this was about diatomic molecules, okay. Now when we talk about polyatomic molecules, say we have CH4, okay. Now in CH4, what is going to happen is that if you see CH4, it is simply going to get dissociated into carbon and hydrogen. Now but it won't dissociate just in one step. This will be a multiple step reaction, wherein CH4 will first lose one hydrogen, so we'll have CH3 and hydrogen, okay. Now for that, in that case, what will happen, the bond enthalpy for the first reaction will be different, correct. Then again what we are going to do, we are going to take the previous product, that was CH3. From CH3 then another hydrogen is going to get loose, so we'll have CH2 and H. So in that case again the bond enthalpy will vary, because our initial products are only, our initial reactants are only different, correct. So now what we notice here is that this gives us a series of bond enthalpies. So for such polyatomic molecules, we say that we take, instead of taking the dissociation enthalpy, we take the mean bond enthalpy, okay, because we have various reactions happening simultaneously, as well as we have various bond enthalpies over here. So in that case, what we simply do is that we add all of these together, okay. On adding, the final answer that we get is the mean bond enthalpy. Next we have the lattice enthalpy. Now lattice enthalpy of an ionic compound is the enthalpy change which occurs when one mole of an ionic compound dissociates into its ions in gaseous state. So now for lattice enthalpy, if we say, it is mostly for ionic compounds, okay, firstly. Secondly, that it occurs when one mole of only ionic compounds, they are dissociating into their ions, not into their atoms. They are dissociating into their ions, that too in the gaseous state. Simple example is Na plus and Cl minus. It will dissociate into Na plus and Cl minus. Now since it is impossible to determine lattice enthalpies directly by any experiment, we use an indirect method, that is to construct something known as the Born-Haber cycle. Now let's look at what is this Born-Haber cycle. So in this we have a series of steps, okay, a series of steps which yield a series of enthalpies. So if you look at the first step, we have sodium that is in solid state which goes to its gaseous state. So that process is sublimation. So we, in the first step, we have sublimation of sodium metal that is happening. So its enthalpy of sublimation is 108.4 kilojoules mole inverse. Then in the second step we have now this gaseous sodium that we have. Next step, we are dissociating it into its ions, correct. So this Na to go into its ionic form, we have to make it lose a electron. So it will lose an electron, that is it will become Na plus, and here one electron is lost. So this is called as ionization of sodium atoms. So here again the ionization enthalpy is what, 496 kilojoules mole inverse. Next we have the chlorine, that is the second part. Same thing is going to happen. Here now we will have dissociation, because Cl2 is already in its gaseous state. We are going to just simply dissociate it to give us one atom of Cl. Here the bond dissociation or the bond enthalpy will be 1 to 1 kilojoule mole inverse. Lastly, we will again need a Cl, which is there, which is an atom. We want it in its ionic form. So we make it gain an electron and acquire a minus sign. So here we have electron gain that is happening by the chlorine atoms, and the electron gain enthalpy here is given as minus 348.6 kilojoules mole inverse. So now when we want to combine all of this to find the lattice energy, that is, we apply the Hess's law and we add all of the enthalpies that are present, okay, and we get a total lattice enthalpy of positive 788 kilojoules, okay. So that is how, using the Born-Haber cycle, we find the lattice energy. Now here we can also find something else. Along with the lattice energy, we can also find the enthalpy of the solution, okay. So before that, we will look at what is exactly enthalpy of solution. So enthalpy of a solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. So if you look here, we have delta, that is enthalpy of solution, and we have the lattice enthalpy, and we have the enthalpy of hydration, okay. So this is what we are saying, is that here it is the enthalpy change that occurs when any, say, 1 mole of substance, it is dissolved in some specified amount of solvent, that is, say, this enthalpy of hydration, and this is the lattice and this is the solution. This is what we have to find. So say now this is what we have, NaCl, that salt we are dissolving in some amount of solvent. So we have to find now the enthalpy of the entire solution. So we know for 1 mole of NaCl, lattice enthalpy we already calculated, that is 788 kilojoules mole inverse. Now by literature we have to remember that the hydration enthalpy is minus 784 kilojoules mole inverse. So if you do the subtraction part over here, we get enthalpy of solution, that is 4 kilojoules mole inverse. So what we can say, that the dissolution of NaCl, it is accompanied by very little heat change, because it is so less, see, 4 kilojoules mole inverse. This is like very less, like comparatively. So on dissolving so much amount of NaCl in certain amount of solvent, this is the heat, that is heat change that occurs. Now next we'll look at enthalpy of dilution. So it is known that the enthalpy of solution is the enthalpy change associated with addition of specific amount of solute to the specified amount of solvent at constant temperature and pressure. This argument can be applied to any solvent with significant modification. Now enthalpy change for dissolving 1 mole of gaseous hydrogen chloride in 10 mole of water, it can be represented by following equation. So previously what we were doing, we were taking that amount and we're dissolving it in something. Now here we can have multiple steps. For convenience, we use the simple aqueous for water. So we are dissolving this HCl in water, first 10, then we are going to 25, 40 and infinite. So what is happening, if we see that the values of delta H show general dependence of the enthalpy of solution on the amount of solvent. So depending on the amount of solvent, you see the delta H, that is the enthalpy, also varies. As more and more solvent is used, the enthalpy of solution approaches a limiting value. That is the value in infinitely dilute solution for hydrochloric acid of the solution delta H is given in S3. It is minus 74.85. If you see, initially there was quite major changes that were happening. Then it started to remain constant, like, and then on infinite dilution it remained at only minus 74.85 kilojoules per mole inverse. So if we subtract the first equation from second equation, that is this equation S1, if we subtract from this, we can say that we are, this value is minus 0.76 kilojoules per mole inverse of enthalpy of dilution. Now, it is the heat that is withdrawn from the surroundings when additional solvent is added to the solution. So the enthalpy of dilution of solution, it is dependent on the original concentration of the solution and the amount of solvent that is being added. Okay, so that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.